So we reject the null hypothesis in favor of the alternative hypothesis. The alternative hypothesis is that the treatment appears to be effective, or that the treatment is effective, and so therefore our conclusion would be that the treatment appears to be effective. Now notice that, remember, this example 10.6 was really the same example as 10.4, same data, same scenario, we just use a different hypothesis test. And this is the opposite conclusion that we reached with the sign test. That may be a little disconcerting to us. We may think that all hypothesis tests should come to the same conclusion, but as this illustrates, that's not necessarily the case. And so you might ask, well, which test should we believe? Which one should we trust the most? Well, we should really trust the test that has the most power. And in this case, the signed rank test has the most power, and so we'll trust that result maybe a little bit more than the sign test. And so based off of this result, it appears that the treatment is indeed effective. Now our last type of non-parametric test is called the Kruskal-Wallis test. Again, this is named after the statisticians who devised this test. And the purpose of this test is to compare 3 or more populations. And specifically, we're going to compare 3 or more population medians. So it's similar to one-way ANOVA that we talked about in Chapter 7. In ANOVA, we compared 3 or more population means. So this is going to be a non-parametric version of this one-way ANOVA. The formal hypotheses that we're going to test in this Kruskal-Wallis test are: the null is that the population medians are all equal, and the alternative is that they are not equal. Very similar to the ANOVA test, only stated in terms of medians rather than means. Okay. Informal, the hypotheses are that the populations are the same versus the populations are not the same. This is kind of the terminology that the book uses. This is what they really mean in a little more formal terms. So to illustrate an example of this, let's look at example 10.8 from the textbook. In this example, we are comparing the albumin levels in adults following different low-protein diets. Now, these albumin levels are used to measure whether a person is getting enough protein. If a person goes on a low-protein diet, then we might suspect that they aren't getting enough protein in their diet, and so we're trying to assess whether that's the case. And so here's the data. Now what we've done here is we got 3 different diets. We've got one that's we call a 5% protein, a 10%, and then a 15%. And so the first person on the 5% protein diet had an albumin level of 3.1. The second had a 2.6, and so on and so forth. So these numbers are the albumin levels of these different patients on the different diets. Okay. So we have 3 independent populations here. One population is all people on the 5% protein diet, the second is all people on the 10% protein diet, and the third is all people on the 15% diet. We want to compare those 3 populations using this these three samples of data. Okay. So the question is there a difference between the median albumin levels of these 3 populations? Okay. So the formal hypotheses that we're going to test in this example are that the 3 medians are all equal versus the 3 medians are not all equal. And so to do the calculations here, these calculations are rather complicated. The book talks about how to do them, but I've built this into this worksheet, Kruskal-Wallis. And so over here we're going to enter our samples of data. We set this up so that we can have as many as 5 samples of data, but in reality we could have any number of samples. And we could also have more data values in each sample. I've just shown a portion of the entire spreadsheet here in this picture. And so we enter our samples of data over here in the yellow. This here calculates the sample sizes. This is the total number of data values. And then over here it ranks things, and then it does these intermediate calculations down here, and then over here we get our test statistic, which is denoted H. Now we're going to use this test statistic, we're also going to need to know the sample sizes. So keep all those numbers in mind. In order to come to our technical conclusion, we're again going to use a traditional method. Our critical value comes from Table 8 on page 286. The criteria that we're going to use are given here. We reject the null hypothesis if the test statistic is greater than the critical value, and we do not reject the null hypothesis if the test statistic is less than or equal to the critical value. So this is kind of opposite criteria to what we just saw in the Wilcox and signed rank test. But the reason they're different is because this test is set up in a different way. So when you're doing your homework, make sure you're using the correct criteria for these different hypothesis tests. Now here's Table 8 from the back of the book. We see it's titled Critical Values for the Kruskal-Wallis Test, and it gives two different significance levels, 0.05 and 0.01. Now this table is a little bit difficult to read the first time you see it, and so we've got here either 3 groups, 4 groups, or the table also continues on the bottom and on the next page with 5 groups. So in this case we've got 3 groups. If we were comparing 4 different populations, we would use this set of columns over here, but 3 groups. Now below that it lists N1, N2, and N3. Those are going to be our sample sizes. Well, if you remember from our data, we had sample sizes of 3, 5, and 4. Now which one we call N1, which is N2, and which is N3 isn't terribly important. What they've done here is listed these so that N1 is the biggest, N2 is the middle, and N3 is the smallest. And so we're going to look at N1 equals 5, N2 is 4, N3 is 3. And so we look about halfway down here. We have 5, 4, and 3. There's our 3 sample sizes. And then we're going to look under the column alpha equals 0.05, and we get our critical value. So again, 5, 4, and 3, those are our sample sizes, and there's our critical value, 5.656. Okay. So there's our critical value. Again, here's our criteria. In this case, our test statistic was 7.52. That's greater than the critical value, and so we would reject the null hypothesis in favor of the alternative hypothesis. The alternative hypothesis is that the population medians are not all equal, and so that would be our final conclusion. So there does appear to be a difference in the albumin levels between these 3 different populations of diets. Now, which diet is different than the rest? Well, that's a whole other issue that goes beyond the scope of what we're going to talk about here. So stated another way, we could state this conclusion as saying that there is a statistically significant difference in the median albumin levels between the 3 different diets. Okay. Just kind of a more lengthy way of stating the fact that the 3 population medians are not all the same. So to summarize our discussion here in Chapter 10, we've been talking about non-parametric tests, which are similar to the parametric tests for means from Chapter 7, but we have no distribution requirements. We do not have a requirement that the population is normally distributed or have any other type of distribution. And so one question you may ask yourselves is, well, how do I know which to use, a parametric test or a non-parametric test? Well, here's kind of some suggestions. If we have a large sample, then use a parametric test. We should really use a parametric test if we meet the requirements. If we have large samples, meaning bigger than 30, then we're always going to meet the requirements for the parametric test, so use that. However, if we have small samples and have evidence that the population is not normally distributed, then use a non-parametric test. Now, in the Chapter 10 homework, we're always going to be using non-parametric tests. Sometimes the problem will tell you which test to use, but other times you'll have to figure out which type of test to use. And so to help figure out which type of test to use, I've summarized our 4 different tests here. The first one was the Mann-Whitney U test, and that's where we compared two independent populations. And so if your problem involves two independent populations where one has no effect on the other, then try the Mann-Whitney U test. The sign test we used where we had data that come in matched pairs, and then likewise the Wilcoxon sign rank test, we had data that come in matched pairs. And so which test to use? Well, the book will tell you which one to use. And then the last one was the Kruskal-Wallis test. That's where we compared three or more independent populations. And so again, you can use this summary to help figure out which test is appropriate for each homework problem.